Good morning, students. In the next theorem, we will show that a closed subspace of a Lindeloff space is Lindeloff. So let us take a topological space X tau, which is Lindeloff space, and A is a subset of X, which is closed. We have to show that A is also Lindeloff. To show that A is Lindeloff space, let us take an open cover of A in X, and that we have denoted by the collection Gi, where I belongs to the index set. So by definition of open cover, A will be contained in the union of the members Gi, where Gi are the members from the open cover of A. Now, this Gi, they are from the open cover. It means these are open sets of the topology tau. So, we can say that each Gi belongs to the topology tau for every I belonging to the index set. Now, let us take G is the complement of A. Now, because A is closed and therefore its complement, that will be open. So, G belongs to tau. Now, let us take the collection of open subsets of X, which we have denoted by the union of the members G and the collection Gi, where I belongs to the index set I. So, X can be written as the union of the members from this collection. So, we can say that this E is open cover for X, but we are given X is Lindeloff space. Therefore, every open cover will have countable subcover. So we can say that there will exist a countable subcollection from this collection E such that X will be covered by the union of the members from this subcollection. Now, let us take a collection E double star, which is formed by excluding the set G from the collection E star. Now, because E star is a countable collection, so E double star, that is a countable subcollection of the collection GIs. Now, because A is the complement of G, putting the values of X here, X is union of B, where B belongs to the collection E star. Now, because the collection E star, that is formed by removing G from the collection E star, so we can say that this set A can be written as union of the members K, where K belongs to the collection E double star. So we have proved A is contained in the union of the members from the collection E double star. So this proves that every tau open cover of A in X has a countable subcover. So this proves that A is a Lindeloff space. Now, next we discuss separable topological spaces. A topological space X tau is said to be separable if it has a countable dense set. Means if X contains a countable subset A such that A is dense in X. A is dense in X means the closure of A is equal to X. For example, if we take the usual topological space, means the set of real numbers with usual topology, then this is separable topological space because it contains the set of rational numbers as countable dense set, because set of rational numbers is countable, and also the closure of the set Q, that is R. So we can say that usual topological space is separable. Now in the next theorem we show that every second axiom space is separable. So let us take a second axiom space X top, and we show that this topological space is separable. Now by definition, because X is second axiom, so there will exist a countable base for the topology of X. Let us take that countable base is denoted by beta, and let beta is the collection of an where n varies from 1 to infinity. This is a countable base for the topology tau. Now let us construct a set D by taking exactly one element from each member of the collection beta. Now because beta is countable, so the set D, that will also be countable. Now to prove that X is separable, it remains to prove that D is dense in X. Now to prove D is dense in X, we show that this D intersects every non-empty open set G. So let us take G, which is non-empty open subset of X. Now we have to prove that intersection of D with G, that is non-empty. Now because G is non-empty, so let us take X belonging to G. Now G is subset of X and it is open, and beta is base for the topology. So by definition, for G belonging to tau, there will exist a member an from the base beta such that X belongs to the existing member that is contained in G. Now by definition of the set D, because D is formed by taking exactly one element from each member of beta, and the members of beta, they are an, so we can say that the intersection of D with an, that is non-empty. So from the equation 1 we can say that intersection of G with D, that is non-empty. This G was arbitrary non-empty subset of X. So we can say that D intersects with every non-empty subset G of X, and this proves that D is dense in X, and also D is countable. So we have proved that the topological space X tau has a countable dense set. So by definition, we can say that this topological space X tau is separable. Now let us see some examples of separable topological spaces. The first example, as we already discussed, usual topological space, that is separable because it contains set of rational numbers as countable dense subset. Now the second example is in discrete topological space. We show that in discrete topological space is separable. In discrete topology is denoted by tau1, that consists of the members phi and x. Now the closure of every non-empty subset of X in this topology, that is the set X itself, and so we can say that X closure is equal to X, and therefore we can say that this topological space, that is separable, because every non-empty set has a countable subset, implies X has countable subset. Now, next example is discrete topological space. The discrete topology, that is the power set of X, means the collection of all the subsets of X. We denote this topology by tau2. And we already discussed in the examples of dense sets that in the discrete topological space, X is the only dense set. So if X is countable, then this topological space will become separable. So we discuss the case when X is uncountable. When X is uncountable, in that case, because in a discrete topological space, every dense set is equal to X. It means if D is a dense subset of X, then that will be same as X. It means X has no countable dense subset in this case because X is uncountable here. So we can say that if X is uncountable, discrete topological space will not be separable. So these were some of the examples of the topological spaces which are separable and some which are not separable.